So what I'll do is I'll start with some background to kind of set the stage against the parametric approaches, and then kind of move from the traditional ones and show you the kinds of trade-offs we have to make in the traditional ones, and then move into the less traditional non-parametrics of the spatial covariance function. And then that's probably as far as we'll get. Then we'll take a break and then talk about the hack estimators later, where we move back into a more formal econometric frame of mind. So the background is spatial autocorrelation, and we all know Moran-Xi, and Moran-Xi requires the specification of a weights matrix, which is typically first order contiguity or some distance band and so on. What if we're interested in how spatial autocorrelation changes with higher orders of neighbors, higher order contiguity, or different distance bands? Okay. This, with the right kind of assumptions, might give us some insight into the kinds of spatial models that are behind the data. So what kind of spatial process? Specifically, the parallel is drawn here between time series analysis of the Box-Jenkins type. I don't know if you're familiar with this, where you use autocorrelation functions and partial autocorrelation functions to try to detect whether it's an autoregressive or a moving average, and what is the order of the autoregression, and so on. The original idea was maybe we can use spatial autocorrelation measures, Moran-Xi, along a similar line, and use patterns in Moran-Xi for different orders of contiguity to assess whether or not the process is autoregressive or moving average. We already had a little bit of discussion of this yesterday. When it's moving average, it's local. So then the autocorrelation should stop, be non-significant, or zero for all practical purposes, after one or two neighbors, as opposed to an autoregressive process, which does not stop and keeps going. So then you would have a smooth decaying autocorrelation function, just like in time series. So the idea behind this is, can we apply this to spatial autocorrelation? And we can. And here let me warn you, the notation, the terminology is very confusing, because this is referred to as a spatial correlogram. There is also a spatial correlogram in geostatistics, and we'll get to that in a few minutes. And it's not the same thing. It's the same general idea, but it's not the same thing in practice. So the spatial correlogram in the lattice data analysis, which deals with discrete spatial units, as opposed to geostatistics, which deals with continuous spatial surfaces, we use Moran-Xi. Actually, more specifically, you use the z-value for Moran-Xi. The z-value is what you get when you subtract the expected value for Moran-Xi under no spatial autocorrelation, and then you standardize by the square root of the variance. So that gives you something that is asymptotically normally distributed, and you can stick it in a standard normal distribution and do a significance test. The reason why I say the z-value is preferred is that z-values are actually comparable between situations, whereas Moran-Xi as such is not, because Moran-Xi really depends on the weights matrix. So different Moran-Xis using different weights matrices are not directly comparable. So you can't tell specifically that one Moran-Xi of 0.4 is stronger evidence of spatial autocorrelation than another Moran-Xi of 0.3. You can only say that in reference to their weights matrices, and the z-value actually takes that into account by incorporating the information about the weights in the mean and in the variance. So it's kind of controlled for that. So I prefer to use the z-values to do this comparison.
So is that the z-value that you can construct from Geoda at the bottom of the Moran-Xi plot?
Mm-hmm. Yeah. So at the bottom of the Moran scatter plot, what you have an estimate of the mean, but this is an empirical mean, and you have an estimate of the empirical variance, so then you can construct a z-value. Now, the z-value you do from the scatter plot is an empirical one. the one that's typically used in these analyses is the analytical one. So then under the null, you know that the mean of Moran's I is minus 1 over n minus 1. And that is the value that's plugged in. And then the variance depends on whether you assume normality or equal probability, and they're different expressions, and typically that's how you compute it and then get the z-values. So the idea of a spatial correlogram is then to compute a Moran's I and its standardized z-value for multiple orders of contiguity and to look at how that changes. Always the motivation being, if we find a patterning in these spatial autocorrelation, that will inform us of the type of spatial process that is underlying the data. In analogy, and I should point out, in only partial analogy to time series. Because in contrast to time series, there is no clear one-to-one correspondence between the pattern of spatial autocorrelation and the process behind it, and part of that has to do with the weights. In time series, it's very clear what it is. In space, the weights play a major role. But the implementation is very similar looking to what you would have in time series. So you have, this is using the SIDS sample data set. We have different orders of contiguity, first, second, third, and so on. For each of these, we get a Moran's I. We can standardize it and compare it roughly to a significance level. So what we see here is a decreasing spatial autocorrelation, and then it's not significant, and then it pops out again at a much larger distance. This is typical for smaller data sets, in that, if you can, I like to think of it as bouncing back. And you can only go so far in higher order neighbors, and then if things are positively correlated with the immediate neighbors, then because of the nature of that, first you get differences, and sometimes it turns negative because the neighbors are similar, but then these other neighbors are also similar, so maybe they're different, and then it flips around. If you're far enough, it becomes negative, and then if you come back yet far enough, it turns back into positive. So you can have that kind of this undulating thing, which is possible. I wouldn't make too much of it. One major problem in smaller data sets, and I would call this a smaller data set, it's 100 observations, North Carolina counties, you very quickly run into problems of thinning out of the higher order neighbors, because you cannot duplicate the order of contiguity. So all the first order neighbors are eliminated from the consideration of second order neighbors. And then all the second and first order neighbors are eliminated from the consideration of third order neighbors. So very quickly, the sample size, if you wish, for which this correlation is computed becomes smaller and smaller. And we'll see this in a minute. It's the same problem with distance bands. As the distance bands increase, there are fewer and fewer pairs of observations that are that far apart, so your estimate for those bands becomes inferior.
I just have a question about the dashed line. Is that at the 1.96?
Yes, I believe it is. So it's
like 95%.
yeah, right. The one thing to keep in mind with this is that, and there is an article, it's quite dated, it's in the 80s sometime, by Neil Oden about how to interpret a spatial correlogram of this nature. And the problem is one that we've already encountered several times, last week in particular several times, is the multiple comparison. In that if you do all these tests, the p-values are not the p-values that you think they are. So if you do 6 of these spatial autocorrelation tests, you should take a target p-value and then do a bound-Ferroni bound type of approximation. So your target, say, to keep it easy, your target p-value would be 0.06. Then each individual spatial autocorrelation coefficient should be evaluated at 0.01, not 0.06. And so that is an issue that you get anytime you do multiple comparisons like this. This is a bound. This is kind of a catch-all correction. And it's not clear at all how in individual situations this is in fact the optimal correction. It can overcorrect, typically it does, and there's a whole literature on how to assess this in multiple comparisons. In the spatial domain, there's just this one paper by Neil Oden, E-O-D-E-N, that discusses this, but this is not used a lot.
I saw in a book of Charisma and Deadman or something like that, there was a correction of the p-value. They said C candidate variables or K selected, multiply that by the p-value, and that's a rough approximation for the inflation of the...
Yeah, there's several around.
Does that make sense?
Yeah, there's a new one, and the name escapes me, but it's a very recent other. It's something about false positives. It's a different way of thinking about it, which is kind of the way the literature seems to be leaning now. There are several of these around in the literature. Bonferroni is the easiest one. Then there's a power correction that is slightly different, and this false positives thing is the most recent one. And it seems to be, Bonferroni is too much correction. You know that. And then no correction is also wrong. So where in between do you fall? And this is a new, I can look it up. The specific reference escapes me right now.
They said that C over K was sort of a rule of thumb, not anything.
No, but this is formal. This false positives idea is a formal approach.
What structure of the model does this suggest?
Well, to me, this suggests a model with a local range of autocorrelation. If you have an autoregressive process, you would see a decay that keeps going. Now, I immediately caution, because there's nothing that says that these orders of contiguity are really the metric that we need for the process. Okay. And this is one way in which the nonparametric approaches take a different perspective, in that they use distance. And distance is a continuous metric, whereas order of contiguity is not a continuous metric. It's a discrete step function. So I wouldn't make too much of it. In fact, there is a little literature on this where it becomes very clear that you can't push this nearly as far as you can in the time domain. But I find it interesting. The way I use this is to see whether how my weights are capturing autocorrelation. For example, specifically here, this might tell us that we might want to combine first and second order correlation in the weights matrix, first and second order contiguity in the weights matrix. And so these kinds of diagnostics are useful when things don't work very well. And this brings me back to what I mentioned yesterday with the SAR-SAR models. If you run a lag model and you keep finding strong evidence of remaining autocorrelation, what you might want to do rather than moving to a SAR-SAR model is look at diagnostics like this. And in that case, for example, what I would do is lump these two contiguities together and then see whether that takes care of the problem. I've had a number of empirical instances where that in fact did take care of the problem. So you use a first order weights matrix in the spatial lag, you test the residuals for remaining spatial autocorrelation, and you find evidence. Then you change the weights matrix to being first and second order combined, and then the evidence of remaining autocorrelation disappears. This is not a general rule, but it's a case-by-case situation where you could address this. Okay, so this is the, if you wish, the origin of it all is looking at how the spatial autocorrelation change if I change the order of contiguity. If we switch to a geostatistical perspective, there's this concept of a SemiVariogram. And a SemiVariogram is essentially interested in looking how the variance of the differences changes over space. And it's a little bit uncomfortable because we're used to dealing with covariances, which are product type moments. Whereas the variogram and the semi-variogram, the difference between the two is the semi-variogram is half the variogram. In geostatistics, a big deal is made of whether it's semi or a variogram. The bottom line is you have to make sure that what you're getting is what you expect it to be. And the difference between the two is just half. So if you have a number that is twice what it should be, then probably you're not reporting a semi-variogram, but a variogram. So that is the difference. If you force stationarity in the sense of a constant mean, then there is a much more intuitive interpretation rather than this variance of the differences, which is the average square difference. Anytime you have an expected value, you can estimate this by an average in the data. And in fact, this is how we proceed. This is a so-called moments estimator of the semi-variogram. Tries to estimate this function, which is a function of distance, of separation, h. You can also bring in direction and other such thing, but we won't go there. Function of distance is an expected value of the square differences, so you can estimate this by taking an average of the square differences. The question is the same as we had before the break. What square differences do we take? Because h is a continuous function. It's just like the density estimation. How do we get that if we don't have multiple observations for each discrete h? So we will approximate this by taking bands and estimate this function in distance bands. And that's the classical approach for a variogram. The method of moments, population moment equation, E for the population, sample moment equation, an averaging over the square differences. So what does this really mean in here? We pick an h, which is now not a specific distance, but a distance bin. So let's say you take 5 miles plus or minus 2 miles. Okay. And then you move to 9 miles plus or minus 2 miles. So you have a 4-mile bin. All the pairs of observations that are within that distance from each other fall into the bin. And for those observations, you take the average over n of h, that's how many of the observations fall in that bin. You take the average of the square differences. So the square differences are the differences between the value at two locations. For example, you have air pollution stations, you have an ozone measurement of all the stations that are within 10 miles of each other. You take the difference of the ozone measures and square it, and then average that. So if you have 5 of those, it's an average of 5 data points. The data points being pairs of observations. So there are n squared over 2 of these, roughly. So that's a lot more than n. All the pairs are data points. There are a lot of issues with this when the data points are not distributed evenly throughout space. Because that means you'll have a lot more points at short distances than at long distances, and so on. It's not going to be uniform. So in the practice of geostatistics, of variogram estimation, a lot has been said and written about how to deal with this. It's just like with the histogram. How many bins or how wide should the bins be? We're trying to estimate this variogram based on varying numbers of observations. So this introduces what we called heteroscedasticity yesterday. The precision of the estimate will not be the same if the number of points in the bin is not the same. And so you have all these kinds of complications in terms of how do we get a good estimate of this variogram model. What the variogram is telling us is, in some sense, how the spatial autocorrelation changes with distance. And that variogram is dissimilarity. So dissimilarity increases with increasing distance. Closer together, the more similar; further apart, the more dissimilar. So that is what the variogram is picking up. Typically, the rule of thumb is that you take at least 30 pairs in each bin, and that you don't bother with the very large distances. As you get very large distances, there are fewer and fewer pairs in each bin, so the variability of your estimate really increases. So one rule of thumb, but this is by no means a generally adopted one, is to compute the maximum distance in your amount between your points and take half of that. And so then the effective range for which you compute the variogram is half the maximum distance. Some other approaches that we've seen, for example, in the GSTAT package, the effective distance, as it's called, or distance of reliability, is based on the diagonal of the bounding box of the data. So not actually the largest maximum distance, but you compute the bounding box of the data and take the diagonal, and I believe it's 1/3 of that or something like that. So these are ad hoc decisions. It really, there's nothing sacred about this. This is just a rule of thumb. What you're really concerned with, in essence, is the thinning of the sample. And at some point, your sample thins so much that there simply isn't enough information in these distance bins to have a reliable estimate. For example, let's say you have a very outlying point, then that point appears in all the large distance bins, but it's by itself. There's only one observation in there, so that doesn't give you any reliability. So typically, you cut the maximum distance in half, and you have 7 to 10, 15 of these bins. If you're lucky, you have 30 or more pairs in each of the bins, and then for each of these you compute the variogram, which is actually not a continuous function but a series of points. So I've connected them here just to illustrate, but in essence the variogram is that point. So that, or the SemiVariogram, is that point. So in the vertical axis, in this case, it's gamma. And this doesn't help. You have to know whether gamma is used as the variogram or the SemiVariogram. And that's the value, on average, of the square differences between the pairs that fall into this distance band. So this is really not, this point, but is this point plus or minus a range on each end. And then same here, this corresponds to a point roughly 8, I guess, plus or minus a band. And so you see them equally spaced. What you're interested in a variogram is to find out at what distance does it become flat. Because flat means there is no more change in the square differences as the distance increases. What we're interested in is finding a relationship between, if you wish, dissimilarity, which is the square differences, and distance. Tobler's law, the closer together, the more similar. So flip that around, the further apart, the more dissimilar. So the SemiVariogram increases with distance of separation. When you reach a point where it, for all practical purposes, remains flat, that is the point where there ceases to be spatial autocorrelation. There is no more effect of increasing the distance on dissimilarity. The dissimilarity remains the same. So this is interpreted, and we talked a little bit about that yesterday in terms of the weights. This is interpreted as a range of the process. So the point arbitrarily taken where you decide, well, from here on it's flat, the distance that corresponds to that is the distance within which the data are spatially correlated. Beyond that point, they are not. There is no more effect. Now, you want to be careful in interpreting this, because these are only point estimates. And as I mentioned a few minutes ago, it's unlikely that the number of pairs in each bin is constant for each bin. So the moment they're not constant, then your average is computed with a different number of observations in each bin. And since the variance is tied to how many data points you use, the variance will change from bin to bin. So the precision of these point estimates is not constant. Put differently, this first one could be that value plus or minus a huge range, whereas the second one is plus or minus a very small range. So then deciding from simply the point estimates where the flat part starts is very difficult to do. You have to have some sense of the variability of the point estimates as well. In traditional geostatistical analysis, you actually specify a function for the variogram, and we'll get to that in a few minutes. But first, I want to move from the variogram, which is a measure, or the SemiVariogram, which is a measure of square difference, to the related measures that are cross-product statistics, and which then give us a second notion of a correlogram, namely a correlogram put in the context of continuous distance rather than in the context of these weights that we just saw earlier on.
In the context of the kernel density, I've seen people use varying bands to get the same number of observations in each bin.
Yeah.
Is it valid to do the same kind of thing there?
You can do something similar here. The difficulty is ultimately relating this to a function of distance. So this variogram estimate you can think of as an exploratory device to get a sense of the rough shape of the variogram. What you actually do in practice is then specify a functional form and estimate the parameters of that form. And so then it becomes a question of how do I get the best estimate for the parameters? Do I use fixed bins or variable bins? It's again a trade-off between bias and variance. You can think of it this way: as your bin widens, you will have greater bias for the individual data points within that bin. The tinier your bin, the closer you are to the distance, to this notion of a continuous function of distance. The wider your bin, the more, in a sense, possible different functions of distance you allow, because the range of distance is larger. But then, because you have more data points, the variability is less and the variance is less. So each time you run into this trade-off.
Your data here are residuals from this fit of a second-order trend surface.
Yeah.
Is that it?
Yeah, and they're residuals to get rid of one problem in variogram analysis, that is a non-constant mean. Remember, we assumed constant mean. If you apply a variogram to raw data, that is often an unrealistic assumption. With residuals, you don't have that problem. They have constant mean of 0 by construction. So typically, one applies variogram analysis to some type of residual, very often a residual of a simple transsurface regression. So if there is one way that you see this, if you run a variogram and you see an increasing slope with distance, that's often a marker for the presence of non-stationarity in the form of a trend in the data, trend being non-constant mean. So then you take the trend out, and what's left, the residual, has a constant mean of 0, and then you work with those for the variogram analysis. So up to this point, we're using square differences. Now if we move to the notion of a covariogram, so it's I find it very confusing. A variogram is about square differences. A covariogram is about cross products. And then a correlogram is a standardized covariogram. Okay. But there's also another correlogram in the lattice world, which is the one that you get with different weights matrices. So when you see correlogram, you don't know right away which of the two it is. You need to know whether it's a lattice context or a geostatistical context. So to get to the covariogram, you need to have some more assumptions, because in the square difference, the means get washed out. You don't need to know the means. I mean, you need to assume that they're constant, but they get washed out. In the covariogram, you actually need to know what the means are. So there is there's more information required in covariogram analysis than in variogram analysis. That's why geostatistics comes out of engineering, mining engineering. And there are a lot of practical rules that our statisticians actually are not that comfortable with, but they're very practical. And one of them is this idea of using square differences rather than the more traditional cross products, because you don't actually have to estimate the mean. Even if it is zi minus its mean minus zj minus its mean squared, the means cancel out. So you don't actually have to know what the mean is. So the variogram, semi-variogram analysis requires less assumptions than covariogram analysis, which is a cross product. But to keep the cross product standardized, you need to subtract the mean from each terms. So you actually need to know what the mean is. That's more, I mean, it's not a lot more information, but it's more information than the semi-variogram requires. So that's why it is in purest mining geostatistics type of approaches, the focus is almost exclusively on the semi-variogram. In the statistical world, we need to move back to moments of a distribution. And the semi-variogram really doesn't fit into that. What we need is a mean, a various covariance matrix, maybe third moments, and so on. So we need to move from the square difference notion to a cross product notion, which fits squarely into our moments of a spatial distribution. One moment of the distribution is this spatial covariance matrix, which tells us how different locations covary. Okay. But to get to that, we need a little stronger set of assumptions. Specifically, we need to know the mean. And then for each distance, we can have the covariance between the random variables that are a distance h apart. So we compare s plus h, which means s being the location shifted by h, with s itself. And we can do this for any distance, including a distance of 0. What we get at 0 is the product of s with itself, so that is the variance of the process. So the covariance at distance 0 is the variance of the process. As you move away from distance 0, the variance decreases. The similarity decreases. This is Tobler again. Closer is more similar, further is more dissimilar, so the covariance goes down with distance. So this is the opposite of the semi-variogram. In the semi-variogram, the value goes up with distance. The covariogram goes down with distance. And then the natural next step is to get rid of scale effects. The covariogram is scale dependent. The correlogram is not. The correlogram is also referred to as an autocorrelation function. So simply, we take, for every distance h, we take the covariance for that distance h. So this is a measure of how the values at locations that are h apart covary. In other words, how similar are they? And we scale this by dividing it by the variance of the process. This is a standard correlation function. In a standard correlation function, we also have a covariance, and we have the square root of the variance of the first variable and the variance of the second variable. This is an auto function. It's the same variable each time, so it's the same variance. So the square root disappears. And that's why we can have C of h over C of 0. So this autocorrelation function we can then analyze as a function of increasing distance. So what happens to the autocorrelation as distance goes up and the correlation decreases? So conceptually, we're in business. We have a function that shows us continuously how the correlation changes with distance. Only we don't have a function yet. So how do we estimate this thing? We have the same problem as with the variogram. We don't have individual data points. We need to group them in bins. And then for each of these bins, we compute the covariance. And the way this is easiest done in practice is to standardize the variables. You take out the mean. You standardize them so that their variance is 1. And then you simply, just like with the variogram, take a bin of a given distance width, take all the pairs of observations that fall into that bin, and compute their average cross product. So you take all, since they're standardized, you don't have to worry about doing the division by the variance. Everything has the same variance, and you simply average them in the band. Okay. And what does that look like then? It looks like something like this. These little dots. So again, these dots are not for a specific distance, but they're for a distance range. And they decrease with distance, increasing distance. Several implementation issues. Just like before, bin width, distance of reliability, minimum number of pairs in each bin. Those are the kinds of things that we are used to by now, and the results will depend on this. And it's always the same thing. It's a trade-off between bias and variance. As the bin gets smaller, your bias goes down, but your variance goes up. As the bin gets larger, your bias goes up, but your variance goes down. One thing we're interested in, and it's actually not that hard to do, is to carry out inference. Remember, with the original correlogram using the weights, I had this kind of one-size-fits-all 1.96, and we had the problem of the multiple inference. A non-parametric way to deal with this is to try to estimate a correlogram function under spatial randomness. So given the data, how are we going to mimic spatial randomness? For example, for Moran Xi in Geoda, this is what happens. You take the data, you compute Moran Xi, then to assess significance, you want to compute a reference distribution, which you get from shuffling the same data around over and over, recomputing Moran Xi each time, and then you get a distribution, and you compare where you are, where the observed value is relative to that distribution. In the correlogram, we do something similar, with one twist in that we use an envelope, a randomization envelope, rather than having an empirical distribution at each distance. This will look familiar to you if you've done any point pattern analysis. This is the same technique used in point patterns to find out whether, say, a k function fits within what the k function would be under spatial randomness. So specifically what we do is we take the data, we shuffle them around, and we compute a correlogram for the new spatially random data set. And we store the values of the correlogram for each distance band. So for each of these, we get a new set of points, and we store it. We do it again, we get a new set of points. After we do this a number of times, say 100 times, then for each distance reference point or each band, we have a distribution of the points that we get, the estimates for the correlogram that we get for the random samples that we created, the spatially random samples. And then we can take characteristics of that distribution, either the maximum or the minimum, or typically to get a 95% interval, you take the 2.5 percentile and the 97.5 percentile, and you pick these out for each distance band and connect them. And that gives you a so-called randomization envelope. Now, all the problems that we have for computing the correlogram to begin with also reappear in the randomization envelope. So don't take this too seriously. This is an exploratory device that gives us some sense of how different this correlogram might be from a correlogram generated for a spatially random data set. And as I mentioned, the same problems are relevant here too, in the sense of how many data points do we have in the bin, how sparse does it get at both ends, at the large distance end as well as the short distance end. One point that I forgot to make that I should mention is you actually don't have an estimate of a correlation for any distance that is shorter than the minimum distance in your point. So there you have no information. So you don't really know what's going on with the autocorrelation at the very short distances. At the very large distances, it's the same. For distances larger than the maximum distance, you have no information in the data set. So what we see here in this particular example is possibly at the very short range, only marginally significant correlation, but this is likely due to high variance at the, since I did this, I know what's going on, and there are very few data points in the shortest distance band. So I would dismiss this as being just a precision issue, but then we have spatial autocorrelation up to a point, and then this is no longer significant. So we can look at these distances, and roughly between 4 and 6, there seems to be a cutoff of no longer having significant spatial autocorrelation, and then we can use this as a way to determine the range of the spatial correlation. So we could say roughly, around between 4 and 6, the correlation is no longer significant. Now, the problem with making a statement like that is that we are assuming and visually interpolating between these points, but we don't actually know what is the shape of the function that connects these points theoretically or for the particular data that we have. So to get around this problem, in geostatistics, different functional forms are assumed. And these functional forms then allow us to actually have an estimate of the correlation at these intervening distance values, which right now we simply don't observe. You can think of this as a histogram. So you take the bins and you compute the value for the bin. You don't have the smooth density function that we really want. You just have a discrete approximation to it. And I did want you to know, in order to put this literature in perspective, that in geostatistics we then come up with these theoretical models of how the variogram should change with increasing distance. The upshot of it is that a theoretical variogram model is a parametric function that has both distance in it as well as some parameters that need to be estimated from the data. The typical parameters that are estimated are the range and then the variance of the process, which is often called a SIL. So these are the kinds of things that you get from the data. But it's very similar to how I started. When you try to describe a distribution, you can assume a functional form, say normal, and then you get the mean and the variance and you plug it in. Same thing here. You assume a function, say spherical or exponential, you estimate the parameters and then you plug them in, which then allows you to come up with an estimate of the SemiVariogram, or as the case may be, of the correlogram at any distance. Given the parameters, you just plug in the distance and you get a value. So you get these kind of nice functions like this. This is an example using pollution data, and this is an example of directional variogram. So we take distance and direction, and for each of these we have these smooth functions. The dots are the actual SemiVariogram estimates for discrete bins, and what is going on is you replace these discrete points by a smooth function. And the range is the point where it turns flat. With these functions, that's always highly stylized, whereas you might have trouble doing this for the actual SemiVariogram points, because you take a functional form, it just fits it through the data in some optimal fashion, some kind of least squares fit or something, weighted least squares typically. And so this is the parametric approach. Parametric in the sense, you give me a distance, I have the parameters of this function, I can give you a variogram for any distance you want, even distances that we didn't use in the computation of the variogram. So this is the parametric approach. Then the non-parametric approach is where you don't assume a functional form. So you don't want to force this structure on the data. You want the data to let you find the function, just as before with the kernel density estimation. So the data inspire the function, and rather than assuming the function beforehand, we get it from some kind of smoothing process. There is one catch here. One of the reasons why these theoretical functions like the spherical variogram or the exponential variogram are so attractive is that they give you a variance covariance matrix that is proper. Proper meaning positive definite. Positive definite is the extension to matrices of the notion of a positive value. Say a variance has to be positive. You can't have negative variances. Positive definite matrix does not mean that its elements all have to be positive. It's actually much stricter than that. It roughly means that the determinant of any submatrix of that matrix has to be positive as well. That's a much stricter requirement than just having positive numbers in the matrix. So the non-parametric approach, the drawback of that is that you have no guarantee from just fitting a function to the data that what comes out of this is actually a proper covariance. In the parametric approach, you get it by construction, because you only pick functions and you only allow parameter values by constraining the parameter space that in fact give you a positive definite variance covariance matrix. So you don't have to worry about it. If you take a proper variogram function, you get a proper variance covariance matrix. In the non-parametric approach, nobody's telling you what to do. It's the data. And so the data can very well provide you with the equivalent of a negative variance, which is a variance covariance matrix that is not positive definite for all the distances involved in the computation. So that's something to keep in mind as we proceed.